Ladies and gentlemen, welcome to chapter 1, part 3, shear stresses in fluids. So, as we learned before, we know that we have a certain shear stress, tau with yx, which is just the dynamic viscosity times a known quantity, the shear rate. And this shear rate is exactly the same like the differentiation of the shear gamma with respect to time. And gamma is nothing else but dx to dy. Okay, so that means that here with the shear stress, we can simply get this is nothing else than mu times d dt of dx to dy. And then, of course, we can make use of changing the differential operators, so d dy dx dt, and we know that the differentiation of x to t is nothing else than the velocity in the x direction, so that is just u differentiated with respect to t. So the stuff here, of course, is nothing else but u. Okay, so that seems to make sense. That is just the definition for Newtonian fluid. And in the more general case, of course, we know that the shear stress is a function of the shear rate. So it is not proportional, but it is just a function, an arbitrary function. And this stuff then is called fluid rheology. And we can determine the function, for example, in a viscosimeter. And then we can get, depending on the fluids, of course, something like that. So we see here the shear stress tau plotted against the shear rate. So du dy is, of course, nothing else but the shear rate. And then we can see three different liquids. Three? Okay, it's hard for me to count. So 4 different liquids. The first type is a Newtonian fluid. And this is just what we saw before, of course. So we have the linear dependency between the shear stress and the shear rate. And the proportional factor, of course, is the dynamic viscosity. And then, of course, it is just also the slope. So if we would like to plot that into the dynamic viscosity against the shear rate, then we would see for the Newtonian fluid that we get a constant viscosity. And then, of course, we can do the same for other liquids. So another liquid, fluid, why do I say liquid? Fluid may be the Bingham fluid. Here we see a so-called yield stress, which you can see here. So, and that means that if we have shear stresses below the yield stress, then we only see elastic deformation. And the fluid behaves like a solid, for example, a toothpaste. And then, of course, we can also do exactly the same in order to get the dynamic viscosity depending on the shear rate, just by differentiating it. So that means that for greater shear straits, because here we see a Bingham Newtonian behavior, so we get a constant value. And for smaller shear stresses, it should tend to infinity. Okay, So this would be the case for a Bingham type fluid, Bingham type fluid, of course. And okay, and we also have two other kinds here. One is the shear thickening fluid. In the case of the shear thickening fluid, we see that the viscosity should get greater if we get greater shear rates. So that would correspond to the case that the fluid gets thicker. So shear thickening. Wet sand, for example. And we have a third case, which would be, let's take this color, if the fluid gets less viscous if we increase the shear rate, for example, in polymer melts. So here in this case, we would get something like that, which is, of course, we will reach a plateau. So this one is shear thinning. And of course, as we know the different scales, we know that all this microscopic behavior, which we can just see here, so the continuum quantity mu, of course, is just a result of what is happening on the molecular scale. Okay, so that is for the fluid rheology. And now the next one would be the relation of viscosity and molecular structure, of course. So we know that the dynamic viscosity mu is the continuum mechanical representation of the molecular transport of momentum. And now it depends, of course, on the type of the fluid, what type of transport of momentum we have dominating. So on the type of gases, of course, we see collisions because one gas molecule collides with another one. And if we have liquids, then the molecules are so close to each other that intermolecular forces are dominant. And that, of course, gives us a hint to what's happening to the dynamic viscosity if we increase the temperature. So if we start with the gases, so let's think we have an air molecule. So the diameter is in the order of magnitude of 10 to the minus 10 meters. We have a thermal velocity, so that's the velocity, the mean velocity, of course, to the Brownian motion of around about 500 meter per second. And we know that we have a free path length. Mean free path. So that's the distance one molecule has a free flight before colliding with another one. So 1,000 times the own diameter. And from thermodynamics, of course, we know that as a result of Brownian motion, of course, the thermal velocity is a result, is proportional to the root of temperature, and the mean free path is proportional to the temperature, the root of that, up to -1. So what will happen if we increase the temperature to gases, to the molecules? Of course, we will see, of course, more collisions. So if we increase the temperature, then we will see more collisions as the speed raises up, as well as the free path gets down. So here we also see not only more collisions, but also a greater transport of momentum. Okay, that is exactly what we see here. If we increase the temperature, then also the dynamic viscosity increases. But for liquids, we see we have the opposite correlation. And now let's have a look why this is the case. The reason is that for liquids, we see long-range molecular interaction. So we see here long-range van der Waals forces. And so we see here the force Fr depending on the radial distance from one molecule to another one. So here, of course, we would see one molecule. And that means that we have two parts. We have two parts for molecules with a greater distance with the attraction. And if they get very close to each other, for instance, if the electronic shells start to overlap, then we see repulsion. And here we also get an equilibrium distance. And now, of course, it's quite simple what happens. You can just think about if you increase the temperature, then of course the Brownian motion increases and the distance from one molecule to the next one increases somewhat. And if the distance increases, you can see it exactly like here, then the van der Waals forces decrease. And if the forces decrease, then of course you have a smaller transport of momentum. And that is exactly what we see here macroscopically. We see that for greater temperatures, we see that the dynamic viscosity of liquids starts to decrease. And of course, this correlations, both of them, should also hold for the transport of heat. So that means if we have lambda against temperature, it should decrease for liquids and increase for gases.